Okay, good morning, dear colleagues. So I think it's time to start. And it's a great pleasure to introduce today's distinguished speaker, Dr. Rodolphe Jazzar, a leading researcher in the field of organometallic chemistry and molecular catalysis. Please join me in welcoming Dr. Jazzar.
Thank you so much. This here. All right, that's a very kind introduction. I didn't know there was so much to say about me, so thank you so much. All right, before I start, I want to thank a few people because I'm not here. I'm here thanks, let's see how this works. Does it work? Maybe not. Oh, here, it's coming. I'm here thanks to Lucas. Lucas introduced me to Open Readings. He didn't tell me the full story because he told me it was a student-run conference and I should not be too worried. It's actually a high-end students-run conference. I would say it compares well with international conferences that I've seen in the level of the speakers and also in the organization. I want to thank Jugas for coping with me because I don't answer well to emails. It's faster to reach out by WhatsApp, strangely enough. And he was kind enough to adapt to my needs. I also want to thank Goda, Martinez, and Povilas, which are only a small part of all the team that I've managed Open Readings, but they are the ones that I've maybe interacted with the most. I came to know that Martinez, for example, is not a basketball player, as a lot of people tend to think. Povilas told me about something about Lithuania that I didn't know, that at some point there were book smugglers in this country where you were trying to protect the language. And I think that's important for me to learn. And I want to thank Bob Dylan. And you're going to ask me why Bob Dylan, because I was trying to find who were famous people that had connections with Lithuania. It turns out that Bob Dylan is from Lithuanian descent. Maybe you knew, maybe you didn't, but I thought it was nice to know. All right, where I'm from. Are you familiar with Asterix and Obelix? Okay, great. So thanks a lot for that. So if you're not familiar, it's French cartoons. They drink a superpower drink and they become super powerful, and then they go and beat up the Romans. And so they live in this small village up there, and they have all the Romans that are around it. And you're going to ask me, why am I showing this? Because I live in California. Oh, I forgot the colors. There you go. So I feel sometimes like I am a girlish person, and I'm surrounded. I don't have a magic power, but we are trying to do our best. All right, if you have not been to San Diego, it looks like that. In San Diego, we have 3 research institutions. The first one is Scripps. And so you have 2 Scripps. You have Scripps Research and Scripps Oceanography. There are 2 different things. Scripps Research, where you have people like Jing Kuan Yu, Phil Barron, and so on, which are leading in organic chemistry, is a private institution. And Scripps Oceanography, although it has the name Scripps from the Scripps family, it's actually part of UCSD. The second institution is UCSD, that is very close to Scripps, and very close to the beach as well. And finally, you have SDSU, San Diego State. And so all these 3 institutions drive research locally, totaling, I think, around 100,000 students altogether. Amongst different fields. You also have 2 additional private universities, but with a smaller smaller populations of students. That's a picture I took. It's actually from my house right now. So living in San Diego is great. And everything that you've seen about California is true. So if you want to come and visit us, please come. We have the beach, we have the sun, and we have the research. All right, enough about San Diego. A bit about me. All right, so this has disappeared. I am French, but I'm not from France. I tend to not talk about it too much because it leads to long stories, as some of you have seen last night. But I'm actually from West Africa. This is where I was born and raised. And I generally share this with my students at the university because I have a very diverse population of students coming from various immigration profiles, as you can imagine in the States. And I like to remind them that I can relate because at the age of 14, I took my first job. I worked as a kitchen because some teacher at school told my parents that I was too stupid to do into education or learn anything. As I found out, I was dyslexic. And as I found out, I actually had a superpower. That means I can't write the same way as people do. I always make mistakes, but I can process data better than a lot of people. And I'm sure some of you here in this room have the same superpower that I have. You have the ability to see a lot of data and find a connection. And that's a particularity that dyslexic people have. Anyway, so in Togo, you have nothing to do in terms of science besides mathematics. So I'm a math major. And well, I really wanted to go in the UK after my bachelor. And so the only opportunity was for me to shift to chemistry because the Erasmus program to go to the UK was in chemistry. So I switched track. That was a good decision. And so what I'm going to do is at the end of the talk, if you can tell me why I switched to chemistry and why I enjoy chemistry, you are winning this. So, which is not American chocolate, because if you've tried American chocolate, you know it's pretty bad. This is, I think, Dutch chocolate. I'm not sure, but it's quite good. Anyway, after that, I've traveled a lot, but you've already heard about that, so I'm going to skip it. Right now, I have 3 positions. I work for the CNRS, which is my primary affiliation. I'm also a non-Senate faculty at UCSD. That means I don't have an official position at UCSD, but I do teach and I do research. I'm also recently an associate professor at San Diego State. And I'm trying to build connection with friends, mainly at the moment. And San Diego State is willing to follow me on that idea. All right, it's been an intense week. I don't know for you, but for me, it's been an intense week. I've realized that open readings, it's all about exposure. And this week I've been exposed to fields of research that I knew nothing about. And I'm sure it's the same for you. We've heard about material science and laser physics. I didn't know about, I mean, I kind of heard about ultra-fast lasers, but I don't even know how you can be faster than the speed of light. And I found out by talking to the speaker that you can actually be faster than the speed of light. So I've learned something this week about that. We've learned about antimatter in a way. Maybe I'm not sure it's the right term. About helium-free and anti-helium-free. We've learned about space, Voyager, and so on. And that was fantastic because I really related to that, even though I don't know anything about it. And we learned about biology. And specifically yesterday, I was like blown away by talks about what's the correct term? How basically to look at women's breast and trying to understand and locate cancer cells and so on, or the brain. I work with this. That's my playground. So I'm kind of connected to all of these topics, but as well, not really connected to these topics. I think I have a different perception. If you're a physicist, you're probably thinking that the periodic table is just a very narrow view of the world. If you are a biologist, this is just some things that you don't consider, but then you are seeing the larger picture of it. And I'm really interested in one specific atom of the periodic table. I do play with the others, but mainly I'm considered a specialist of carbon. And what I want to do today is pick your brain. Have you heard about carbon allotropes before? Probably you have. Okay, can you tell me which ones are these two? Diamond, and what is the other one? So diamond is at the top. Graphite, right? So charcoal, basically. So these are two forms of carbon. So that's why a carbon allotrope is a different form of carbon. And here you have a few of them. That's another form of diamond, because you have a different crystallization for diamond, and therefore you will have a different configuration for diamond. Okay, and that's other forms of carbon that has become popular as well recently. Me, I'm mainly considered or interested into a different form of carbon allotropes, so I hope you will follow me on this. So if you are going to undress the carbon atom from the octet, okay, so that's tetravalent carbon here as an octet, it's filling the octet rule, and if you undress carbon, you can access carbon allotropes. One of them that is very popular is carbon radical, and where you basically formally removed an electron, but now you have another field of reactivity that is specific to carbon. If you remove another electron, you have carbenes, which is my main field of research. And finally, if you remove 3 electrons, you're going to have carbene. All of these carbon allotropes will have reactivities that are very specific to their electronic configuration and unique as well. All right, let's talk about singlet carbenes. So carbenes, because it has 2 electrons, can exist in 2 states. You have singlet carbenes and triplet carbenes. I'm on a Mac, so if it's not showing well, it's because I'm on a PC right now. Forgive me for that. All right, what's the difference? In the singlet carbenes, you have 2 electrons that are in the same orbitals. Okay, so that means that these 2 electrons can both be sigma donating. So that means they can give electron density or electrons to a metal or another atom. And they can also accept electron density from the atom. And that kind of creates a bond with the elements they bind to that is can be more or less strong depending on how much sigma donating it is or pi accepting. The triplet carbenes have 2 electrons that are in different orbitals, and therefore they behave as diradical. Most of the carbene out there in the field are mainly singlet. You do have some triplet, but triplet carbenes are hard to characterize and access. But you have a plethora of singlet carbenes, and my talk today is going to focus on singlet carbenes. All right, I'm not going to surprise you if I tell you that carbons are everywhere around us. I mean, they compose, I think it's the 3rd element on this planet that is the most present. And therefore, carbenes is the same. Every carbon atom in every organic molecule, you could think about it as a precursor to a carbene. Maybe not these ones here that right here, because it's difficult to make carbene there because the carbon is already saturated. But any other ones, you can think about putting a carbene there. All right. Slow. It's not going anymore. It's stuck. Thank you. All right. So we can say that the ubiquity and diversity of carbons in organic molecules in general, you can find in carbenes. And that's very important because that means that you can also tune the reactivity of a carbene. All right. What I want to show you here is that all the fields that we've seen these weeks, you will find carbenes in these fields. And it's not necessarily obvious. You find carbenes in materials. I think that's the easiest one. Okay, carbenes are used across the chemistry field, but also the engineering field for OLEDs, for creating materials that conduct electricity, for creating materials that are magnetic. So there are many applications of carbenes in this field. That's not surprising because chemistry and material science, maybe not laser physics, but then again, I'm not sure, we are well connected. Where it might not be as obvious is space. And in space, you have a lot of carbene that exist naturally, I would say, floating in space. The question as to how they are formed, that's a different question, but we had a speaker that actually addressed that point on Wednesday. So you have carbenes that are floating in space, and at the beginning of carbene research was how we can make in a lab something that exists naturally in space. And that's a tricky question, because they exist in space because they are not going to react with many things. When they meet one another, they might do, but they might take a few centuries to meet one another, or millions of years. In nature, I'm sorry if my pictures are not showing so well. All right. You're familiar with vitamin B1, maybe? It's a vitamin that we have in the body that is right here. What you might not be familiar, and I actually teach that to my students in my OChem class, is that the behavior of vitamin B1 is actually very close to the behavior of a carbene. So it's considered that a carbinoid. It will react like a carbene. It's not a carbene because you are in vivo, so you can't have the free carbene itself, but you're going to display all the reactivity of a carbene. And then you have some very nice work that has been reported by a famous Nobel Prize, where you have an iron carbinoid here as well, species that is doing carbene reactivity using an E molecule. All right, what do we do in our team? I'm going to give you some example. We're interested in mechanism. Ooh, this is terrible. Okay. See, that's why I should have done on PC, on Mac. All right, that's okay. All right, so mechanism. We are interested in trying to understand how carbenes react and what they can do. And one way to do that is to actually look at the mechanism. I know people are not always concerned by mechanisms, but if you are actually taking the time to learn from looking at the mechanism of a reaction, you can do new things. And that's a good example here. We know that carbenes can do an oxidative addition. So oxidative addition is when a metal is going to cleave a bond. Okay, you're breaking down the bond, and formally you are doing an oxidative addition because you're oxidizing the metal. Carbenes behave as metals, so that they can get oxidized. So a carbene, you can think about it as a carbon in the oxidation state 2, and when it does the oxidative addition, you go in oxidation 4. Okay, so you can break bonds. We've shown as well that you can eliminate. So do something that metals do that is called a reductive elimination. So you're reducing the oxidation of the metal and you eliminate it with a molecule. What metals do well, it's activating carbon monoxide. It turns out that carbenes can also activate carbon monoxide. So here we have a pattern where we see that carbenes and metals can have similar properties. Of course, they don't have the same electronic configuration, so it's a very different field. But what we were curious about is whether we could capitalize on all of these to do a catalytic reaction. And so what we described a few years back is the first carbonylation reaction done at a carbon center. And normally they are all done at a metal. And so we were just able to capitalize on this mechanistic work to demonstrate that you can use a carbon and do a full cycle of a catalytic reaction. So is that useful? No. I mean, I'd rather take a metal to do my carbonylation reaction because the turnover number, which is the number of times the catalyst will turn around the catalytic cycle, is going to be tremendous. In this case, it's 5. Okay, so it's not a good catalyst, but it works. So it's a proof of concept. Another thing that we are interested in is chirality. So again, we designed this system a while ago where we had this carbene precursor. We generated the free carbene, and what happened is that the free carbene is so rich that it wants to insert in the trityl bond of a CH. That is right there. And you get this molecule. And what we realized looking at the molecule is that we had like a propeller shape. And if the carbene is chiral, then the propeller is chiral, and we wondered if maybe we had chiral luminescence from this molecule. And it turned out that yes, it's actually a decent CPL molecule, so it displays polarized light emission. And is that going to revolutionize the field? Probably not with this molecule. But now if I put it into a little bit of prospect, it has the same properties of a molecule that has been designed for this use, but that takes way longer to make. So if you can start looking at the carbene and thinking that this is a precursor maybe for some of your use in your own lab, maybe you can design molecules that are maybe less difficult to access, but that will display reactivities across a broader spectrum. Okay. We're also interested in main groups. So as I told you, carbenes can activate EH bonds, okay, reversibly, oxidative addition, reactive elimination. And we've recently used the chiral carbenes. It turns out that nobody in the field has wondered how a chiral main group molecule is going to activate bonds. Very simple ideas. It's just nobody thought about it. And so we were lucky to be the first one to publish this work. I heard last week that people in Lausanne, colleagues in Lausanne were, in Switzerland were very upset because they're also working in this field and they didn't think about it. It's not a super smart idea, okay? But we were very interested to study if we could trigger an enantioselective reaction in this case. So basically, if you have a chiral carbon right here, how is it going to react with this EH bond? And what we showed is that you have full retention of chirality during the oxidative addition. It makes sense because you are basically attacking the carbon atom that is close to the chiral center. However, what was less obvious is that we could extend that to other hetero elements like phosphorus and silicon. And if you look in drugs that are coming out in the market nowadays, you have a lot of drugs that contain chirality that is not on a carbon atom, that is on a heteroatom. So you have p-chiral phosphorus, okay? And here we were able to show that we can generate an enantiopure p-chiral phosphorus from a racemic phosphorus element molecule. And so that was exciting to us. And what was even more exciting is we can do the same with silicon, because silicon is a completely different way of activation. You go through a silicon 5, so your carbene is going to sit above the silicon and insert in the bond. All right. What I want to do today is tell you a bit more about what we do in nanomaterials and catalysis. All right, so as I said, carbenes can be both pi-accepting and sigma-donating. That means how are we going to look at them? And so what we do, and here I want to give you some tools if you're interested in carbenes, if that's something that you want to do for yourself. How should you look at your carbenes? The number one parameter you should look into is the singlet triplet gap, okay? So you want to know what is the energy between the singlet state and the triplet state. That will tell you a little bit more about the electronic configuration of your carbene. The second thing that you want to do is look at the HOMO-LUMO gap, okay? You want to know what is the gap from the HOMO-LUMO. That will give you another parameter to study your carbene. And so what we can do, I'm very sorry about the quality of the pictures. If I look at this carbene here, the saturated NHC, I have the singlet triplet gap, HOMO-LUMO gap, and if I put in front of this carbene another one, like the CAX, what you're going to see is that you've narrowed the singlet triplet gap and the HOMO-LUMO gap. What essentially it tells you is that now the CAX are more sigma-donating and more pi-accepting. That means they are going to bind to metals more strongly. But that also means that the carbene carbon is also more nucleophilic and more electrophilic, which can be a problem or it can be an advantage. All right, and what we can do is we can basically do that. So here I did some computation, so this is unpublished. I was curious to see if we could compare aryl carbenes to one another and what kind of profile we would have. And so I played a little bit with one of my students and we were able to have a profile for all this family of aryl carbenes. Many of those have not been described yet. Okay, so we can see where we want to go and we have an understanding of the electronic properties of this carbene. Another parameter that you want to look into is what is called the steric profile, how big it is, okay? Because if a carbene is very big, then it's going to influence substituents that are going to bind to it, but also all the chemistry below it. All right, so one parameter, if you've never played with Samba VCAT, that has been developed by the Cavallo group, I encourage you to do it. You don't need X-ray data. You can do it with DFT data. And what you do is you just extract the XYZ files and you feed it into the program, which is online, it's on the web. And you can look at the structural environment, the steric environment at a given atom. So you select the atom, and then you look at all the environment around it. And this is great, because it's great for me as a carbene chemist, but if you're an organic chemist that is looking at some a nucleophilic attack or electrophilic addition, same thing. If you want to know how the steric is going to influence your reaction, you can just calculate one of your intermediates and feed the XYZ data into the program, and you will have a nice steric map. So steric maps, sorry, they look like this. Sorry. So here I have an example. So we have the tris-adamantyl phosphine. So it's a phosphine with adamantyl groups, pretty big. And what you can see is that if you are sitting right at the phosphorus, you feel, and that's why it's red all around, the steric of all the atoms around the phosphorus. You are like crushed by the steric profile. If you go a bit further, and here I model what you would feel if you were a copper atom bound to this phosphorus, then you feel it much less. If you are a carbene, and you can see differences, this is why I highlighted both of them, you can see that as a phosphine, all your substituents are sitting on the top. Okay, besides the Buchwald type phosphines where they have ligands that are dangling down, like this one, John Phos. But in the case of carbenes, most of your substituents are facing down. That's something that if you are interested in working with carbenes, you need to take into consideration. Because again, it's going to influence the reactivity below the carbene center. All right, the way I think about it is if you are a phosphorus atom or phosphorus ligands, you're an inverse umbrella. Everything is happening above, so you can be a metal. Below, you won't feel too much the influence of the ligand, at least from a steric standpoint. If you are a carbene, well, you're actually controlling what's happening at the bottom. Okay, so you are an umbrella. All right, these electronic parameters and steric parameters, they can be both complementary. Sometimes they work together. And sometimes they are antagonists. They fight one another. So if you are going to use a carbene on a ligand as a metal or a carbene for organocatalysis, think about this, because it will make a big difference in your reactions. Oh, that's terrible. Okay, if you want to characterize a carbene, how do you do it? So let's say you found a molecule that has not been characterized as a carbene before, and you want to tackle that problem. What you should try to do is there are two methods. Either the carbene is stable enough, and you can characterize it by standard spectroscopic methods, NMR, X-ray, EPR, and so on. Or it's not stable, in which case what people do is they do trapping reactions. And actually, trapping reaction is at the core of the history of carbene research. Like in the 1900s, the first reactions with carbenes were done by trapping reactions. They didn't know they had a carbene. They were taking a carbenoid structure, so the carbon may be bound to a diazonium, a diazo. They were irradiating the species, generating a carbene. It would react with an olefin, for example, an alkene, and you would make a cyclopropane. They didn't know they had a carbene. They knew what they had to begin with. They knew what was the product. And so that's a trapping method. You're generating carbene that you can't see, but you characterize it by the product that you have. Okay, so that's the other method. What I'm inviting you to do if you're interested in working in this field is make sure that you're characterizing it well. Because carbenoid reactivity and carbene reactivity, sometimes it works in the same direction, but sometimes it's antagonist. That means you are going to get the wrong data out of it. So ask yourself the right question. Do I have free carbene? Am I seeing carbene reactivity? Or on the contrary, do I have a carbenoid and I'm seeing something else? And I will give you an example. So there's some really nice works from the Schneider lab in Germany, where they basically prepared this nice platinum complex. They crystallize it. They put it on the X-ray. They irradiate it with a laser. And they get to see the nitrogen that is flying off. And if you read that paper, it's super nice, because you can actually see in the X-ray structure the N2 molecule, nitrogen, that is trapped in the lattice. And so we can see the free carbene and slowly nitrogen moving in the crystal structure. And so they have the crystal structure of the first molecule, they have the crystal structure of UC of this one. And finally, they characterize the crystal structure of this compound nicely. Another example to show you the difference between a true carbene, like this one, and one that is not a true carbene is if you take this carbene precursor, you generate the free carbene, you will bind it with copper only in this fashion. That means you're going to put 2 ligands on the carbene center. If you do the same through what we call a carbene reactivity, you're going only to put 1. And that's essential because it tells you about the activation of the carbene center, but also tells you what you can do with it. If you are looking to do catalysis with copper and you are trying to make copper 1 monovalent, you're not going to do it from the free carbene. You have to go through the carbenoid. And that's essential because you might try a reaction and you see it doesn't work. It's not a catalyst, but actually it would be a catalyst if you had used the right method to prepare the corresponding compound. By NMR, it's going to be very difficult to differentiate the 2 species. So you need to, again, ask yourself the right question here. All right. Okay, that's very blurry. Okay, we're going to talk about carbenes in catalysis. All right, when a carbene interacts with a metal, it donates electrons, accepts electrons. So the way I'm going to do it from now on, I'm going to represent it as an arrow that goes from this doublet of electrons toward the metal. Okay, it's just a nomenclature that we follow. You might be familiar with this scientist here that passed away a few years ago, Professor Bob Grubbs, that is well known for his work on olefin metathesis. And I think he's the most representative person when it comes to the importance of carbene chemistry, because this catalyst is used worldwide. Okay, there's a major competitor here in Poland, not too far. There's a major competitor in Germany as well, not too far in this field. Each time you see a windmill, it was very likely made by this catalyst, which is, to me, amazing to know that the catalyst that I actually make in my lab could be used to make these things. So it's a big market. Big market means there's high interest, at least from our competitor in Poland or in Germany. And the other way to look at this problem is to think about carity. Okay, carity is important. I mean, we have a few Nobel Prize to tell us about it, and more recently we have 2 more, again, on the importance of carity in organic synthesis. And we were puzzled by this sentence from Glorious a while ago that was basically calling out all carbene chemists and telling them, well, if you're a carbene chemist and you're interested in carity, maybe you should look into that problem. Because there's a lot of carbene structures, but as you can see around the carbene center, there's always 2 nitrogen. So essentially what Glorious is telling us is that out of this small subset of known carbenes, and this is just a small subset, these 3 here in blue have not been reported in their chiral form, either because there is no use, or it's because nobody has tried to show that there was some interest into studying this. Actually, what I'm going to tell you is if you are really interested in this, all E1 in pink are also not known from their chiral version. And you're going to tell me, why is that important? Well, if I look at the CAC here, which can also bind to ruthenium quite well, the CAC variant of this is big money. It's actually used right now for the ethanolysis of olive oil, any kind of oil you can think about, because it performs super well. We are talking about over 700 turnover number, so that's the number of times the catalyst is turning by itself, to make fuels, plastic lubricants, and also detergents. So compounds are basically used directly by the industry. Okay, that's great. But why is the chiral carbene interesting here? Well, it turns out that every single patent that is reported for ethanolysis using CACs is showing a structure that is not chiral. So if you make the chiral version and it works as well or better, then you're kind of bypassing every single patent out there. So now there's an interest. So it turned out that synthesis of chiral CAC is not that hard. There are many ways to trigger an asymmetric configuration around the carbene center. You can change what's on the nitrogen, and the Kramer group in Lausanne has actually worked on that. You can introduce chirality here in the backbone, or you can introduce chirality closer to the Carbenes center on the other side, which is the route that we took. All right, so the first thing that we looked at, after seeing the glorious work, and I'm very slow, I'm sorry, is that we realized that there was a carbene that had been reported. This Carol is from the Carol pool. It's derived from mantle, but nobody had shown that it was going to do any kind of asymmetric induction. So we prepared the copper complex of this. We tried it in this catalytic reaction, and we found out that it is not good, an anti-oxidative catalyst, which we attributed to an inversion of the mantle ring that can flip. It's actually energetically accessible, this flip of the ring, and it probably kills the enantiosis activity. So we thought, all right, if it's a problem of the flipping, maybe we can make something more rigid. And that's what we did with cholestanol here. So we did the first total synthesis of a carbene. I don't encourage you to do that. It's a lot of time, unless you have really a use, which was our case. And we got the X-ray structure that showed that we had a configuration around the carbon center that was rigid and should induce a quadrant. So if you're not familiar with asymmetric catalysis, if you want your catalyst to be a good catalyst for asymmetric transformation, you need quadrants. So that means you need to be able to look at the metal center and define space where you have accessibility or steric hindrance, because it's going to direct where your molecules are approaching the metal center. And so luckily enough, in our case, we were able to obtain 55% enantiomeric excess, which means that it is a chiral carbene. So it works. The idea works. It's not the best catalyst for this transformation, but it actually works. All right, we have since reported the preparation of the enantiopure form of this ligand family, which we have also patented for the reasons I told you before, because there is big money involved in this field. We've developed the catalytic applications and show that they do display some very good enantiosis activity in a number of transformations, which I'm not going to discuss today. So we kind of validated that there was a problem. We were in a way called out by Glorious, telling us that we should do our job and try to answer that for the field, and we have. And I'm telling you today that there are many more carbenes, because it's not directly what we do in my lab, chirality or asymmetric transformation. There are many more carbenes out there that needs to be developed in asymmetric transformations. So there is a field here for somebody interested. What I want to talk about now is carbenes in nanomaterial. Have you heard about the Mosh civilization before? Anyone? So I was reading this article because sometimes I'm bored in the plane and I like to read things about where I'm going. And in this case, I was going to Peru with my family. And the Mosh civilization basically is one of the first civilizations around the world, and I think the Chinese have done it as well, that was able to do plating. So a lot of the copper artifacts that you would find in Peru at the time were not actually pure gold. And I'm very sad for the Spanish that came and stole all the gold. They were actually copper artifacts that were plated with gold. And they had found a way, using the tools, the chemical tools that they had at the time, to plate copper with gold. So they would make solutions of gold by dissolving it in strong acids they were able to make. And then they would dip their copper artifact in the gold and plate the artifacts. And that triggered questions to me is, how does this work? And so I looked through the literature, and I couldn't find somebody that actually looked at that from an homogeneous standpoint. So if you are a material scientist, you probably know about this, and you probably understand how it works. But me, as an organometallic chemist, I had no clue, and I couldn't find anyone that really tried to address the problem. And so one way to look at this is if I take this M11 surface, is that you are going to have atoms that are going to approach the surface, like let's take silver here, and the most electronegative element, silver in this case, is going to pop out an atom of copper from the surface. That's the idea, at least from my very basic understanding of this process. And so we thought, okay, can we make M11 copper trimer? can we reproduce in solution something that exists in the solid state? And so what we envisage is maybe we could stabilize a copper trimer with carbene bonds. And so we prepared a trimer that has this kind of carbene bonds. And so we also have the copper-copper bonds. So these are called, in this case, it's a 2 electron bonds between each copper, and you have 4 centers. So it's a 4-centered 2 electron bonds. There's 2 electrons shared between the coppers. There's also 2 electrons shared with the oxygen. All right. If you reduce this compound, this trimer, you're going to get a low valent copper. Now you have something that is analogous to our M11 surface. And the next question that we had to ask ourselves is, can we exchange one atom of copper for a more electronegative element like silver? And the first thing that we did is not silver. We looked at gold because gold is easier. And what we found out is when we did the reaction of this copper trimer with this gold monomer, we obtained this. So not only we displace one atom of copper, we displace all of them free. And we were super excited about this result because not only we displaced all of them free, but we actually didn't break the compound. And I would have expected this to just go sideways, like be some of the reactions that we have in the lab where we just have black tar because the reaction didn't go in the way you want. And in this case, we realized that the copper-copper bonds are probably stabilizing the metal-metal interactions and holding this cluster together. And so it works, it's just you are displacing all of the atoms. Now, what about silver? So if we do the same with silver, we have the same results. We're able to displace all of the copper atoms for silver. And now, because gold is more electronegative than silver, we can also displace all the silver by gold. So essentially, we can take a trimer of copper, exchange all the atoms for silver and then for gold, while retaining the structure altogether, which is sort of exchanging free atoms on the surface by retaining the configuration. All right, so did we validate the idea that we could actually reproduce a surface reactivity in this plating of gold? I think we did. We understand now that it does follow the rules of electronegativity in this type of complexes. The next question we had is, does it really display the properties of a surface? And if you want to do that, you have to look at electron maps. And what we did is we took this complex and we ran the electron maps. We calculated how the electron density is around this trimer of copper. And okay, you can see here, I think this presentation is against me today. You can see that there's a small triangle right there. So these are the same electron density map that are calculated for an M11 surface, so for a metallic surface. We see exactly the same trend with our system. So we are actually mimicking well the properties of a surface. Of course, there are other things to consider here that are not considered in this evaluation. But we can see the trisynaptic basin, which is this triangle here, not only in copper, but also in silver and gold, which mimics what you would see for a gold, silver, and copper surface. All right, so we kind of validated what we were trying to achieve, and okay, I'm on time. And then we thought, okay, where can we take this story further? Okay, so we were wondering if we could do something better with this. And so we realized that in carbene nanomaterials, and there's a lot of carbene nanomaterials that are developed every day, especially with the Cruden group in Canada and the Tasuya group in Japan. None of them is metal hydride. And we know that metal hydrides are super important because you find them in batteries, you find them in your cars in some cases. And so we did a literature search, and we only found one, at least for copper, carbene stabilized copper hydride. In this case, there are 31 atoms of copper, 6 hydrides that have not been localized. They were determined by analytical methods, and 3 carbene bonds. Now, metal hydrides with copper are well known. Okay, they are well studied, and you can find a lot of clusters of these species in the Cambridge database, the X-ray database. And what you will find is that in every single cases of them, which explains why we didn't find so many of carbenes, it's stabilized by sulfur bonds, phosphorus bonds, and so on. And so we felt that maybe we could contribute in our way to this field. And we set our eyes on this compound. So this is the reagent of the year, it's the striker reagent. If you're an organic chemist, you maybe used this reagent before because it's used for the reduction of carbonyl bonds and olefins and so on. And you can buy it from Aldrich, 1 gram for $110. So I wouldn't say it's very affordable, but it's okay, given the price of chemicals these days. And so how would you go at trying to make a carbene variant of this striker reagent? Number one method that you could think about is do the reduction of a monomer. So you prepare a stable monomer, you reduce it with a hydride donor, and in principle, you should get the hydride species, and that's actually how this striker reagent is made. You make the phosphorus copper chloride, you reduce that phosphorus copper chloride with hydride reagent, in this case, it's a borane hydride reagent, and you are going to get the corresponding copper hydride species. Now, we prepared the corresponding monomer and also reduced the corresponding monomer with a carbene, but in our case, we got a massive mess. Like we had copper deposit on the NMR tube for the reaction, on the shanks, a disaster. So we can't do it from the monomer. There's a good explanation for that, is because you very likely make the copper hydride, but because the carbene we are using in this case is so amphiphilic, so nucleophilic and electrophilic, the hydride migrates to the carbene center, and eventually the whole thing falls apart. All right. Another option that you can have is ligand exchange. Okay, so you're going to take a well-defined cluster, a well-defined species, and you're going to exchange one ligand for another. Basically, you take a ligand that wants to leave, and you bring in a ligand that wants to bind. And so that's how you can do it for this cluster here. If you take this U25H22 phenylentroline phosphine ligands, you can displace all the phosphines by phenylentroline, or most of the phosphine, no, all the phosphine by phenylentroline, and you get this nice species here. We thought maybe we can do the same. Maybe it's that easy. So we took the striker reagent, and we added our carbenes. So carbenes are more donating than phosphines, so in principle, you have a worse ligand and a better ligand. They should displace one another. But it didn't work for us. And for the same reason, I think, is because you generate the copper hydride, somehow you break down the cluster, and we only got degradation. All right, and this is when we had inspiration for our first project that I just presented. We thought, okay, maybe we can rely on these metal-metal bonds interaction and capitalize on them. And we envisaged that maybe these metal-metal bonds would stabilize the cluster during the aggregation part to make this cluster. And so we would have a situation where we start from a well-defined trimer with 4 Sutter 2 electron bonds. We have a carbene stabilized species, so we are stabilizing these intermediates. We can do a control reduction, and because we also have the carbene stabilized bonds, we can control the aggregation. At least that was the rationale. And so we tried. It doesn't always work like that, I'll be honest with you. We have a lot of failures in other attempts for other things, but in this case, it worked well. And so we were able to obtain this 6 carbene 14 copper H12 complex. That was unexpected. All right, now we have a new carbene copper hydride species. We have the striker reagent. How do they compare? So the first thing we did is we compared the stability in air. So if you bought striker reagent and did not store it in the glove box, then you wasted $100. Because within 2 hours in air, it is gone. You won't be able to use it. You won't be able to capitalize it. It's too reactive. It reacts with air. Hours can last for months, and we basically try to understand why. And the carbene stabilized the complex, making it resistant to oxidation, which we proved by electrochemistry. And we also compared the powder X-ray data from a compound that we prepared on day one and the same compound several months later, and it remains unchanged. So that means this cluster is quite stable. All right, but why is it quite stable? So one way to look at this, and I'm going to invite you to look at the hydride atoms, okay? Fix them, and you will see that in the one that is stabilized by the carbene, which is this one, the hydrides are not moving. They are staying between 3 atoms of copper. If I do the same for the striker reagents, and again, look at the hydrides, you will see that they bounce. Sometimes they are up to 3, sometimes they are up to 2. Basically, they are changing their coordination environment, which might explain why the striker reagents reacts better, because the hydride is less stabilized. And so you can look at the coordination number around the copper, and in this case, for our cluster, it's always 3. There's always 3 atoms of copper that are bonded to the hydride, and in the case of the striker, it's between 2 and 3. It oscillates. All right, so what you can do if you want to have fun, you can look at these X-ray structures on your phone. It's quite fun, but what you need to look at here if you're going to do this is manipulate this 3D structure to be able to see that you have an interaction of the electron density of the hydrides with the carbene center. And in this case, the hydride is well located around the free phosphorus, but it's not actually interacting with the free phosphorus. All right, now if you've made a new compound that is potentially a catalyst and it's very stable, there's a high chance that you've made a rock. Okay, it's not going to be useful for anyone but yourself. And so what we needed to do next is to test it in catalysis. And indeed, when we compared our catalyst to the striker reagent, it works. There's a caveat. We need to introduce TMEDA. If we don't have TMEDA, our catalyst does not react. So we need to activate our catalyst. But if we activate it, it performs better in air. You can take it from the bench, put it in your reaction, it's going to perform much better than your striker reaction that probably died a few hours ago. And with colleagues at the Scripps, we actually screened through several reactions, and I'm not going to show you all the data because it's too much. We screened this catalyst across 6 different types of reactions, and we actually benchmark its reactivity, and it works well. So you could actually use it in your lab. It's actually easy to make for this type of reactions. All right, what's next? So I'm coming to the end of my presentation, I'm almost on time. I hope I've been able to show you that if you capitalize on the library of carbenes out there, the one that we thought about and others have thought about, or the one that you're going to imagine in your own labs, because there are many, you can design your own system. If you capitalize on the electronic structures and the steric structures of this species, you're going to be able to do exceptional things. And where we are going right now is we are trying to derive ideas from these 2 concepts, structure, electronics, to make materials that are photoluminescent. And that's why I need collaborations here. I saw many posters this week that I think tells me that I need somebody here to interact with, because I don't have the means to make the devices and to study the properties of the species. We can make them. We can maybe study their luminescence because we are equipped for that, but we can't take it to the next step. And I would be very interested to see if there's somebody to initiate a discussion with about taking this to the next step. Then other things that we are looking at is nobody in the field has any idea, but not just for carbene, for phosphines as well. Why you take a ligand and suddenly you have a cluster with 20 atoms of copper, the next one you have 2 atoms of copper, the further one you have 16, it's a black box. What they know is that you take a monomer, you put a reagent, and sometimes you have a reaction that is reproducible. Often you don't have a reaction that is reproducible, but you isolate enough material to move on. So we want to try to find a rationale around this. So we are systematically studying how our trimer, stabilized by different carbene ligands with different electronic profiles and steric profiles, are going to control the formation of a species. So we already have a copper-36 hydride, where we just changed the electronics of the carbene center. And we've reproduced the one that we already have with different carbenes. So we know that the carbene family, the CAC carbene family, will generate the same type of clusters. We also know that using different carbenes will generate species that are bigger. We are trying to see if we can go smaller and if we can draw that rationale that we are interested in. All right. I want to thank all the students that I am grateful to work with. I have fantastic students, motivated students. I'm a first gen, and I didn't talk about it at the beginning. So in the US, Americans love to put a tag on everything. And they have a tag for what they call a first gen. A first gen is somebody that is the first in their family to graduate with a degree. I'm the first in my family to have a PhD, but I'm also the first in my family to have a high school degree. Okay. So I'm a first gen. Most of my students, if not all of them, I think besides Patrick and Francois, most of my students are first gen. Okay. So they are the first in their own family to graduate or will graduate with a PhD degree. And I like this quote from Asimov. The true delight is in finding out rather than in knowing, because as scientists, what we love is chasing a problem. Generally, when we found the solution to the problem, we are less interested in it, and we want to move to the next problem. That's how, at least, I feel about this. I want to thank UCSD, the CNRS, and San Diego State for allowing me to do all this research, and all of these people for collaborations and funding, and you for your attention. Thank you. I still have the chocolate, so why did I choose to do chemistry?
Okay, thank you very much for a really beautiful overview of the field, I guess for every taste. So I'm sure we have plenty of questions from the audience.
I have a guess that it started when you were going to Peru to find out how to actually, what are the connections between the cuprum and the gold, and my guess is this.
It's not that. It's much before.
Okay.
It's way, way before, when I was still in Africa.
And may I ask then a question?
Sure.
I'm interested in reusability of your catalyst because, well, I'm coming from a field of thermochemical conversion, and it was quite popular to use char catalysts, activated char catalysts impregnated with different metals, transition metals usually, and the problem was that the usage time was very limited, that you can't recover the catalyst basically. So I'm interested in how many times maybe you can use it, and if it is recoverable, or if you know this answer yet.
That's an excellent question. So for the copper system, we can't because it's homogeneous. So unfortunately, it's a one-shot reaction, but we are using copper that is inexpensive. However, if you are interested in that, this manuscript that we just submitted, which is an iridium complex. So we are also working on the supported heterogeneous system that is supported on charcoal. It's perfectly reusable. But now I'll be honest with you, the use of the carbene here is probably very limited because when you are charring compound, basically you're stabilizing with the carbene, but you're basically killing the complex at some point. You're just helping, the carbene is probably just helping in this system to bind the rhodium to the char. So it works, it's a reusable heterogeneous catalyst, but the effect of the carbene is limited, besides making the material.
Okay, thank you.
Any further question? Carbenes, please.
Thank you for an interesting talk. I really enjoyed it. So I'm actually very interested in the fluorescent properties of the carbene compounds. So can you comment a little bit more on the properties like fluorescence, phosphorescence, maybe the late fluorescence, and the possibly the applications in OLEDs?
So we have published with the Thomson Group at USC the carbene, so the CAC5 up there, copper, silver, and gold carbazole that have 100% quantum efficiency, my memory. So that works. Now, their group, and we don't work together anymore, is heavily interested in this because we are collaborating with a company that is called, I forgot. If you're interested, I will send me an email or we can talk after. I have the information. A lot of the carbenes that they looked at that are here, but they are mainly NHCs. So there's a lot of carbenes that we haven't considered. So the playground to develop more carbazole variants of this copper, silver, gold, and maybe achieve as much or better optical OLEDs, in this case, is there. But what you need is really to understand the electronic properties. This is what they are not doing enough in their lab, from my understanding.
Only became very efficient only with the complex, with the metal, or? So
it's in solution, and in their case, they also have engineers in their lab, because I got to visit them a few times, that prepare the device. So they can make the OLED device and actually study the device, because the company that they work with, that is financing most of their research, actually is only interested in making the device.
But these are phosphorescent or fluorescent materials? I mean, they emit from the triplet state, or?
They emit, they are CPL, so it's CPL transmission. I think they are fluorescent, from my understanding. I have limited understanding, so don't quote me on that.
Okay, thank you.
More questions? Over there.
Thanks. That was pretty early on in the presentation. There are no page numbers, so I couldn't remember. There was something about making them more electrophilic and nucleophilic at the same time.
Yeah. So the DAC is a pure acceptor. The CBA next to it is a pure donor. So with the CBA, you have a pure sigma donor. So you have something that is analogous to CP as a ligand for metals. In the DAC, you have pure acceptors. So the kind of chemistry you can do, if you think about it, is has a massive range, because you can capitalize on two. Most carbenes are a bit of both. And so you need to understand their electronic properties to see if you want to capitalize on the more donating aspect or the more accepting aspect. Now, the problems of having a pure donor or pure acceptor is, of course, the bonds that you're going to make with certain elements are either going to be super strong or super weak. So you have to capitalize on that.
Thank you.
No chocolate. Okay, so you're going to win the chocolate if nobody else has a question.
So we still have some time, so please take the opportunity. Yes.
I'm just for the chocolate. So I have a theory. Is it related to the superpower you mentioned in the beginning?
No.
Then that's it.
Okay, thank you. There's one more there.
Catch it.
I'm also here for the chocolate. So, did you choose chemistry so you could go to the UK? Because you mentioned you wanted to.
I did. I chose chemistry because I could go to the UK, but this is not why I enjoy chemistry.
Okay.
And think about it, we all enjoy the science that we do for a specific reason. Sometimes it's not what you think, so ask yourself the question.
Thank you for outstanding talk. And my question is, I guess, not actually related to the carbenes itself, themselves, but to the change of those copper atoms to silver or gold. And you mentioned that after the change, the structure of the compound is not changed.
Yes.
But the size of the atoms is different, and the size of the atoms, I guess, gold is 30 or 40% bigger, and the bond distance is also longer for gold-gold interaction than compared to copper. So have you considered that in terms of that the structure was not changed, or is it not relevant at all?
It is relevant because I think it changes the whole catalytic properties, because what I didn't talk about here is that the copper catalyst is a very efficient catalyst for the reduction of CO2 to CO. And the copper doesn't work. Sorry, the gold doesn't work in this case. So it will for sure change the reactivity, because you are changing the whole the whole electronic environment around these atoms is very different from copper to gold. But the overall structure doesn't change. So we do have an elongation of the bonds, that is correct. And actually the parameters for that triangle closely match those that you have on the surface, but not for silver. And I think it's due to quantum effects that are not well represented in our trimer with respect to the surface.
Okay, and now what relates to chocolate. Born and raised in Western Africa, I guess you were very keen on the understanding of higher power. So my guess would be you chose chemistry because you wanted to be a creator yourself.
That's an interesting aspect. It's not the case, but yes, but I like the idea. We keep it. No one?
Okay.
Okay.
More questions?
So I will give the chocolate to the first person, and I will tell you why. I enjoy cooking. All right, this is a simple idea. I really enjoy cooking. Okay. That's why.
That's good. Okay, I still have some questions.
Sure. You wanted the chocolate?
I
have another one.
No, I'm cool. I guess in some following slides from this point, you showed the CH in, oh, maybe it's actually backwards. You showed some CH bond activation, intramolecular.
Yes.
I think is the very first example of chemistry slide.
Yes, I remember it.
You remember?
Here.
Yes. It's a very nice example, but can you give us a broader view how limited this chemistry is? Is just the intramolecular type of reaction, or it's also applicable to intermolecular?
It's not just intermolecular, because essentially what we are doing here is intramolecular. This is also Carol. I didn't talk about it too much because I wanted to put the focus on the main group reactivity, but this is Carol. We are doing a Carol insertion. So here you have a carbon atom. So you could think that if you're using a tritium, that also has a configuration that could be a propeller, you should be able to make CPLs from these carbons.
And in this example with silicon, it's actually very nice because you create two consecutive centers.
That is correct. And we control both.
Yes, and you control both. So it's, and also what is nice, I think that your carbene is related with pyrrolidine scaffold, which makes these products are also useful. Otherwise, if you take something too exotic, it would be perhaps just the fundamental insight.
Maybe I can give an idea, something I thought about, and I'm for sure not equipped. Maybe somebody else here wants to take it upon it. I like this because if you are going to do catalysis with palladium and you're going to do CH insertion with palladium or CH functionalization, you're going to use a base. Okay? And here, to make the carbene, we use a base. But we don't use palladium. And so I always thought if there was a synthetic chemist that is more into making drugs and all, I would make carbenes and let them react within themselves, form bonds and structures by intramolecular reactions that actually template what you would find in the core structure of natural products, for example. Because now you completely offset the metal. You're still using stoichiometric amount of base to generate your organic molecule, your carbene. So I think there is a story to be told. Not one that will be told in my lab, but if you are interested in such things, then that's maybe something I would explore.
And how basic are these carbenes?
That's an excellent question. I didn't present that with scale, so if you're interested, we have a paper where we've scaled the basicity of carbenes. Let me see where they. Yeah. Oh, there you go. All right. Okay. So as I said before, on that question, CBA is a pure sigma donor. It's a super base. So the CBA with 2 oxygen, beta to the carbene carbon is more it's more basic than P4TBU, the organic base, it's more basic than the Schrödinger base. And with nitrogen, it is more basic than the P4TBU, which has a pK around 38.
DBU?
TBU.
TBU.
Not DBU. P4TBU, the phosphoramidate.
Okay. These go up to maybe 4. I don't remember.
They are, I think, 38. And so basically for the CBA, we located the pK between 36 and 38. We don't know exactly where it is, but it's a super base. And he explains why, if we want to make the free carbene of the oxygen stabilized CBA, you can deprotonate with KHMDS. If you want to deprotonate the nitrogen stabilized, that is more basic, you need BuLi. And BuLi has a pK around 40.
Yeah. I see.
So they can be super basic.
Nice. And in one example, you said that sometimes, starting from the same precursor, you can have a true carbene species and sometimes like carbenoid species. And it was an example with potassium HMDS and potassium acetate, I believe, as a base. So how I should represent for myself that carbenoid type species in that reaction?
Also an excellent question. That's before. Is it? No, it's further. Sorry. Where is it? Oh, yes, further. It's right here.
I guess
I went too fast. I'm very sorry for the. So what you can see here is that in the case of the copper, you form it's something that you see with palladium. You do concerted metallation deprotonation. And it's actually done with pivalate very often for palladium. In this case, we have acetate, so we are close. And so basically what happens is that you are going to form the copper acetate. And then the copper will basically add to the iminium. So you're never actually forming the carbene in this case. And there are many examples out there. And my advice is look at the base. If the base that you are using, which is the case here, is not basic enough to generate the carbene, then it's very likely a carbenoid pathway.
Concerted process, yes. Okay. And the last question is from these nice metal clusters that you just showed. Do you have any clue about the mechanism?
How they form?
Mechanism, how it's replaced, keeping intact the whole triangle?
Yes. So for the trimer, what we think is actually happening is you're going through a tetramer. So as I showed here, when one atom of silver is coming on the surface to chase one atom of copper, the first thing that happens is that it's going to integrate on the surface. And with what we think is that you have this copper trimer, you have an atom of gold that will sit on the top of the copper trimer. So you have basically a tetrahedral structure, and you're just popping out while doing ligand exchange, because you need to exchange the ligand. You're popping out one atom of copper.
Do you think it's possible to see these intermediates by mass spectrometry? And I think in this coordination chemistry, the people were very successful in trapping these very delicate.
If you know somebody, I would love to study that, because we don't have the capabilities. What I can tell you is the formation of the cluster takes a bit of time. And so I can tell you what we've tried, and we failed. So with my students in Lyon, in France, we got some time on the synchrotron in Grenoble, and what we did is we wanted to see if we were forming these aggregates. And so we we made a device where we generated a solution where we are reducing the cluster. So for the big cluster, for the hydrides, we are generating the hydride monomer, which basically grows itself. And we wanted to see all the steps, because nobody has actually any understanding how they actually form. And so we generated them in solution, and then we pass the solution through a capillary, and we just bombarded it with a synchrotron beam. We faced two problems. Number one, we just fried more or less everything. And when we find ways not to fry everything, the capillary that the solution is going through is permeable to air, and we only got degradation. So at the moment, we haven't designed. So we have thought about another way to look at that, but getting time on the synchrotron in Grenoble is not easy, and the student is finishing, so we're not going to pursue that. But mass spec would be a cool way to do it.
Thank you. No more questions? If not, let's thank the speaker one more time.